you serenade us until people start asking questions?
Okay.
They could use some relaxing guitar music. Tomorrow's the final. What?
Nothing.
Miller's here. Jess likes your music. I like it too. Questions, you gotta go. Okay. He's having to practice for a concert this week.
Next week.
Next week. All right. Let's see. Hi, Jasmine. Bye, Brandon.
Toodles.
Bye, Brandon's guitar. That was Brandon. Levels of unsaturation. So levels of unsaturation is just anytime you're missing hydrogens basically from a molecule, meaning you have double bonds, triple bonds, so any kind of pi bonds, or a ring. So if you have 1 pi bond, that's 1 unit of unsaturation. If you have 2 pi bonds, that's 2 units of unsaturation, etc. If you have like 5 rings in a system, that's 5 units of unsaturation. So you can basically look at it and predict it that way. So for example, if you look at the molecules I have up there on the screen, the top one on the left is a benzene ring. It has 3 pi bonds in it and the ring, so it has 4 units of unsaturation. Okay. If you look at the structure here, oh good, I can highlight that. If you look at the one there, it has 1 double bond. Even though it's a carbon-oxygen double bond, it's still a double bond, and that makes it have 1 unit of unsaturation. Now, you can use mathematical formulas to come up with units of unsaturation. So we went over those in class. If you have questions about that, you can ask that specifically. I can go over those again. But in general, you just kind of have to follow those pretty basic math equations, the arithmetic. Now, as far as acid-base reactions go, I actually have 2 up on the screen right now. These are 2 that Lauren and Stacy, I think, are the ones that sent these to me, and they came from a previous exam, and they asked not actually about the acid-base component, but about the following question, which was, can you draw resonance structures of any of the molecules above? And there's actually 3 main molecules you could draw resonance structures of on there. And so I'll start off, I guess, by going through the acid-base chemistry component of this, since you have a question on that. So the first thing that you really need to do is basically decide or attach pKa values to these. You could equally do it with pKb values, but you know, we generally look at it from the weak acid to conjugate base component, like what I'm going to be doing here. So if you look at the pKa for an amine, which this NH2 is an amine, the pKa for that is up in the 30s somewhere. So it's very, very high in comparison to the things we generally define as acids. The hydroxide doesn't have a pKa because it can't act as an acid. There's no way it can donate that 1 proton it has. And then down here I have a protonated amine, meaning the NH2 has been protonated. It's undergone an acid-base reaction. And a protonated amine has a pKa of about 8 to 10-ish, you know, and then water is about 15. So it's 15.1, right? So we can look at this and kind of identify what's going to be your acids and bases in this situation. Now, we know, like, some of these are going to be common sense, right? Like hydroxide isn't on our acid spectrum. It doesn't even have a pKa, so that's definitely going to be a base. It's going to be our strong base, which means this amine would have to be the weak acid. But even if you didn't know that, you would just pick whichever one had the lower pKa values. That's what's going to be your acid. Wait a second, why do I have hydroxide there? That's not an equation at all that would work. Did I copy that wrong, or was that wrong in the exam? Hold on a second. I thought I copied what they sent me, but now I'm wondering if I had it wrong in the... Sometimes I do have to correct old exams because I... Oh, I see. Yeah, I had that backwards, sorry. Let me fix it. As soon as I start going through and trying to do the acid-base portion, it becomes a little challenging because I didn't have it right. Let's make it so this makes sense, shall we? That's the hope. It's the end of the semester. It's not a good time to get confused on stuff. All right, so 8 to 10, strong base. And then here, if I'm looking at water and the amine, the water actually has a lower pKa. So on that side, this would be a weak base, or actually the conjugate base, and the water would be the conjugate acid. There we go. Okay, so, you know, how did I determine that this is what's going on? Well, the lower pKa's are going to be the strongest acids, right? So if you look at this, the lowest pKa is that protonated amine on the far right or left-hand corner, meaning of everything going on in here, that would be the strongest acid currently on that equation. Or I should say the most potent. It's not a strong acid. I wasn't meaning it that way. Then the protonated amine would be your conjugate base. And all you're having to show in an acid-base reaction is proton transfer, right? So one of the hydrogens came off the NH3 and went onto the OH to give water, leaving the NH2 instead of the NH3. The following equation is kind of the same sort of thing. So you have an alcohol, which has a pKa of around 16-ish to 18-ish. And then a carboxylic acid, which has a pKa of about 2 to 4. And we learned those 5 factors that influence what makes these pKa's what they are. So if you're looking at this left-hand side of the equation, the acid would be the carboxylic acid, and the alcohol would be the base. So I have a weak base, and I have a weak acid. So that means that this proton is going to be pulled off by the weak base. And so on the other side of the equation, you would have basically protonated alcohol, so an oxygen with a positive charge on it. We talked about how the pKa of those would be less than 0, so a strong acid. And then here, we don't have a hydrogen left on there at all, so it's not going to have a pKa. So this would be our conjugate acid, our conjugate base. And if we wanted to show the direction that the equilibrium would favor, and I don't think there's a way for me to show that on here. But if we were trying to show that the equilibrium would be pointing in the direction towards the weaker acid, so the conjugate, or the carboxylic acid would be the weakest acid when you're comparing the weak acid to the conjugate acid. Okay? So if you have other questions on that, ask me. Let's see. Marangeli. I don't know what the... No, I think it was a different problem they were looking at. Did you know know what's the mechanism to make a cyclopentane? No, we did a cyclopropane with carbenes, but not a cyclopentane. I don't know a reaction that does cyclopentane with carbenes, Janae. And why don't we show equilibrium arrows in both equations? Yeah, so if you have a strong acid or a strong base, Stacy, it's going to push it in one direction because it's a strong acid or a strong base, right? They completely ionize and they can completely react. So that's basically the reason. You might say some people that put that as an equilibrium arrow, but the equilibrium would so heavily favor one side that it wouldn't really be something where you'd expect to have much of both. Okay, good, Jasmine, good. Okay, did you show us the mechanism to make a cyclopentane with a carbene? Yes, using an alkene, and it's also in the textbook. So if you have, whoops, there we go. If I have that and a carbene, which is CH2, with a lone pair of electrons on it. So, show it this way. Brandon's still playing guitar. If you guys can still hear that, and if it's distracting, like you can't hear me, let me know. He's in a different room, but I can close the door if we need to. Okay, so the alkene attacks, just like what we've seen with everything else. And while that like hinge is opening, then the electrons from the carbene can come in and attack to the other carbon. And that's how you would get a cyclopropene, or cyclopropane, sorry. And I just highlighted the CH2 to kind of show the same CH2. Marangeli, when completing reactions, what is the best way to know what the starting material was? So, and then what is a good way to know if a hydride or methyl shift? So we haven't actually covered any methyl shifts. They're not in your book, so I just kind of don't go over them at all. All we did was the 1,2 hydride shift. And then if you go over, let's see, if you look at a product, so here, if I show you, let me just do something really fast here, make some room. Okay, so if I have, let me see how I want to do this. Marangeli, this is answering your question on how do we know if a shift happened and such. So let's say I have something like this. And we're basically trying to figure out what the starting material of that reaction could be. Well, there's a couple of different answers for that, and it's basically just practice and working with it to kind of see the different possibilities. So if I'm looking at that, I know, first off, I'm doing my hydrohalogenation. I know that for a few reasons. One, I'm adding HBr, and the product has that added into it. That's the only reaction we've learned that would have anything like that. So you basically need to have kind of a set of things that you look for in every reaction. Like if you have Br2, and then in your product you have 2 bromines, you had to have added those bromines using the Br2. That's what they do, okay? So you basically just have to kind of have those identifiers in your head. Now, what I'll show you here for this one, because I can, let me make sure that this is, okay. What you can have here is a couple different options. So if I added a double bond here, for example, and I add in HBr, I would get the product shown. I'd give you full credit for that. It's an absolutely perfectly valid answer. If instead of the one that I just drew, you drew one like that, you would still get full credit. Okay, it's the same molecule that's just been rotated around that bond that I'm highlighting right there. Now, what if I had that molecule? If I added in HBr, I would still expect that molecule to be the product, okay, basically following Markovnikov's rule. And then lastly, if I followed this one, and I'm going to show the hydrogen here, you would expect that to undergo a 1,2 hydride shift and give you the following product. So this kind of, let's see, 3-methyl-but-1-ene is a really strange molecule for doing addition reactions because the double bond along any of those will still give you the same exact product. But it's basically, you just have to be kind of aware and recognizing those, okay? And that just takes a lot of practice, which, you know, is why you guys have all those problems in the book to work. But if you have something that forms a carbocation, right, and that's kind of what you have to look for a hydride shift. Is there a carbocation intermediate? Yes, it's like continue on the like little arrow path, right? So yes, it forms a carbocation intermediate. Is there a hydrogen adjacent to the molecule that could move over one spot to make a more stable carbocation? If yes, you will have a 1,2 hydride shift. If not, you don't have to worry about it, okay? Now, let me... Okay, so originally I actually drew these acid-base equations at the top because Lauren and Stacy asked if I could cover a question about those really fast from a previous exam. So I'll do that really fast and then answer the rest of the questions. So the question is, can you take any of the molecules from up here and draw resonance structures for them? And there are actually several that you can draw resonance structures for. So remember, with resonance structures, you can move pi bonds and lone pair electrons, and that's it. So on this amine, for example, I can't move anything on the nitrogen because with a positive charge, it means there's no lone pair electrons. However, I can move the bonds in the benzene ring. Anytime you have a benzene ring, you're going to have a resonance structure. This is also the reason why we haven't done any chemistry with benzene yet. The chemistry with benzene is unique. It does not react like other alkenes. Like you would think, you know, why is that not going on there? You would think, why have we not been showing any of these additions going on to benzene? And it's because they don't. Because if you added to some of those, you would destroy the resonance, and resonance is a stabilizing force. So if you break up the resonance, you destabilize the molecule. That's bad. So that's one answer. And then the same thing, you would have a very similar kind of resonance structure with the one up here, because even though this has a lone pair of electrons on the nitrogen, that I don't have shown. Let me add those in. So even though there are a lone pair of electrons there, if they tried to move, they can't, because this bond here, or this carbon there next to it, adjacent to it, is full of sigma bonds. There's nothing there it can move. But you could move the electrons on the benzene ring. Also, another one you could show a resonance structure with would be this one here, which is called a carboxylate ion. It's the deprotonated form of a carboxylic acid. And when you show that, electrons go in. Wow, that's a bad arrow. There we go. And so you would get it's the same molecule, right? But it would have the electrons in a slightly different place. You'd be able to tell this if you like radio labeled one of them, and so one of them was radioactive and the other wasn't. You'd be able to see the difference. But if you just looked at this, I mean, it's the same exact molecule, but they are a resonance form kind of mixed between the two. Okay, so I'm going to delete all that and then go back to the chat box. When I have this screen up, I don't have the chat box up, so. Marangeli, I hope that answered your question with the hydride shift happening. And then Janae, I showed you the one mechanism we learned for the carbene. And then Lauren, can we go over the difference between a meso compound and a racemic mixture? Sure. So let me... There we go. All right, so if I am looking at a meso compound and a racemic mixture. So a racemic mixture just means you have both of the stereochemicals that are that are possible. So let's say I have the R version of chemical X. I don't care what chemical X is. I also have the S form of chemical X. They are mixed together. That is a racemic mixture. Okay? My handwriting is terrible, I'm sorry. That is different than a meso compound. Okay? So what I'm showing you here, that's two different compounds. That's the S form and the R form. They are enantiomers, right? Now a meso compound is if you have, let's say, compound X, and one side of it has an R stereocenter and one side has an S, and it's symmetric down the middle, okay? And so then you also have what you would think would be the enantiomer of that, meaning the mirror image, if you flipped it, would be this. Well, the thing is if you flip that by 100 and... Damn it, Kenny. If you flipped the molecule 180 degrees, it would be exactly the same thing because of symmetry. So a meso compound is singular, compound meaning one, okay? Diastereomers, enantiomers, that's like two. You can have a single enantiomer, which is one of the two types, but a meso compound is just a singular entity. It looks like something that would be chiral. It has chiral carbons on it, at least two of them, but because of a plane of symmetry down the middle, it means that there's no optical activity. Okay, it means if you flipped it around, it would be exactly the same thing as what you started off with. Okay. Alyssa, can I do a Newman projection to a chair conformation and show it flipped? Okay, that'll be a little more challenging because I don't have a model kit. Let me see. I think ChemDraw does have a template for Newman structures. We're going to act like that looks okay. Let me... That's as close as I'm going to get to one of those on here easily. Okay, so let's say I'm looking at something CH3, Br. I'm just putting a lot of stuff on here. Hydrogen, NH2, iodine, hydrogen, and fluorine. That'll work. That's a polysubstituted cyclohexane, right? So if you're looking at this on a Newman projection, the easiest way to go about doing it, and let me find my, oh come on, surely I have. Okay. You guys aren't used to seeing cyclohexanes drawn that way. Let me just see if I can do this by hand. Okay. So there's a cyclohexane. Let me bend this down. Bend that up. That's pretty close to what you guys are used to looking at. And then, oh goodness gracious, this isn't going to work, is it? Okay. Let's just start off with this one, then we'll flip it. So I'm going to, let's see, copy, delete, and swap us over where I can. Okay. Hopefully you guys are able to see this. Let me know if you're having trouble visualizing anything that I'm doing, but obviously, this is not a perfect way of doing office hours or anything, but it's close, and we get to interact with each other, which is kind of nice. I can't fit this many of y'all in my office. Okay, so pull up my little brush. Okay. So, Alyssa, and everyone else, the first thing that you have to do is identify where you want your carbons to be, okay? Now, generally speaking, this one here and this one here would be the one down, the one down here, and the one up there, okay? So the one pointing down is the one pointing down, the one pointing up is the one pointing up. It should make sense, okay? Now, if I want to color code that, because I know some of you guys like that, here. Down, down, up, up. Okay, so now I have to identify the other components, okay? So what you need to think of is when you're talking about a Newman projection, a cyclohexane, you're generally looking down that carbon-carbon bond and that carbon-carbon bond. So the two, or the four that you haven't already color-coded are the two that you're looking down, okay? And so if I were to take that chair conformation, just turn it a little, and look down it, that would mean the purple one here would be there. And then the red one would be there. I hope that that's clear. Then the ones behind it would be there. colors. There. All right. So that's what you're looking at. You're kind of looking down that, and it's much easier, obviously, if you're looking at it with a model kit. That's how we've done it before. But even if you don't have a model kit and you can align it that way in your brain, you can still fill in the rest of everything else that you're missing. Okay? So if you look at the purple carbon, the one I have right here, okay, what is attached to that? A bromine. It's pointing up, right? Let me do this. Oops. If he sees me smiling, my husband's playing my favorite guitar song right now. Makes me happy. Okay. All right. So, getting back to that question, the purple one. What is attached? Well, let's do the blue one first. What's attached to the blue one? Hydrogens. So I don't have to show those. The purple one, what's attached to the purple one? A bromine and a hydroxyl group. Okay, well, if I go through and I draw basically all of the bonds that you're expecting here. Did I get them all? I think I got them all. So here I have a hydrogen, here I have a hydrogen. The yellow one has 2 hydrogens on it, the one in the back. The purple one has a bromine and a hydroxyl. The bromine's pointing up, so I have to show that as the one pointing up, and the hydroxyl's pointing down. Got it. The orange one has a hydrogen and a methyl group. Hydrogen's pointing up, methyl group is pointing down. Okay. The turquoise one, the one that's pointing behind, has a hydrogen and an amine on it. The amine's pointing up. There we go. And then the red one has a fluorine pointing up and an iodine, because I just went the whole gamut and made all kinds of stuff. Okay? So that is how you can look at a cyclohexane Newman projection and convert that to a chair conformation. You also have the ability to draw the flipped form of the chair, right? So that would be my flipped form of the chair. I'm gonna try and make a little more room. Okay, so here I can do the same sort of thing, put on all of my bonds. Okay, so the blue one that I started off with is now pointing up, right? Because when you flip the chair from here, you go like that. So the one that was pointing down is pointing up, and the one that was pointing up, which I had yellow, is now pointing down. Both of those still have hydrogens on them. Okay? The purple one, which is now behind there, okay, it's still attached to the blue, right? That hasn't changed anything. The orange one is still attached to the purple, between the purple and the yellow. The teal one is still right there, okay? The only placement really that's changing is the one that's pointing up and the one that's pointing down. Now, that said, the ones that are pointing up are still going to be pointing up, and the ones that are pointing down are still going to be pointing down. So if you look, I had a hydroxyl group pointing down and a bromine pointing up on the purple one, right? Hydroxyl pointing down, bromine pointing up. Remember, the difference is the change in whether one's going to be axial or equatorial. That's what changes, not whether they're pointing up or down. If one's pointing up, it's going to stay pointing up, but it will go from equatorial to axial or vice versa. The orange one had a methyl group and a hydrogen. Hydrogen's pointing up, methyl group pointing down. The turquoise one had an amine pointing up. Wow, that's getting messy, sorry. And a hydrogen pointing down. And then the red one had a fluorine pointing up and an iodine pointing down. So that is how you do that. I did several examples of that in class, so hopefully it's making sense. If not, it's kind of a little late to get one-on-one help right now. But I hope that one makes sense. And then, I'll just keep that up there for a second. Dennis, is the standard for Fisher projections used to determine the stereochemistry? Or are you supposed to set the projection to the standard? The standard is the standard for a reason. So the Fisher projection you draw doesn't have to fit a standard as it's drawn. But to determine the stereochemistry, you have to make it fit the standard. Does that make sense? So if I have any kind of Fisher projection, okay, I could have it where whatever my groups are like that. Well, I can't determine the stereochemistry of that without going and moving things around, right? So I'd have to move 1 and 4. I'd have to move 2 and 4. Whoops. And so with two flips, that would make that our stereochemistry. So you basically just have to fit those groups to whatever standard you're using. I gave you one standard. I told you guys if you looked it up online, you might find a different one that you could use. I just like doing the 1, 2, 3, 4 since it fits the same type of our configuration we've already looked at before. Lauren wants to know if I can explain antiperiplanar, synclinal, and synplanar. I can. I don't know that it would be any different than how I explained it when I covered it in class, though. Can you tell me a little more about what you need for it? Like what part on that you're not getting, so I know what to start with? I don't like just repeating myself and you guys say, God, she already told me that. I got that part. I'm drawing a structure. Give me a second. Lauren, you still with me, hon? Okay, well, we only really use them to talk about butane, so if you know what they are, then drawing them on butane shouldn't confuse you, because that's what those words mean. So here I drew butane with kind of some perspective. And so what you need to think about is what it would look like down that carbon-carbon bond, right? And you're kind of thinking of a Newman projection. So you're looking down the carbon-carbon bond that's in the middle of the molecule, and you're basically talking about where those two methyl groups are in relation to each other, around kind of like a clock, right? And the reason I say it's like a clock is because there's rotation around that bond that can spin, right? So if you have a model kit, you can spin it around that middle carbon-carbon bond, or any sigma bond. But what you're basically looking at are different energy levels of butane based off of what the molecule looks like in that spinning, okay? So let's draw a couple of Newman projections. The one that I have right now, okay, where I have, let's see, there we go. So this carbon here, carbon 2, is the one that we're looking at right there. This here is carbon 3. That's the one that we're looking at behind. That is a terrible number 3. Okay. So number 1 in this case, carbon number 1 right there, and carbon number 4 right there. Carbon number 1 is pointing down, right? And it has 2 hydrogens pointing up at the top. Carbon 4 has a CH3, or I'm sorry, carbon 3 has a CH3 pointing up and 2 hydrogens pointing down. So what you look at when you see this is the fact that the methyl groups, the CH3s, are opposite to each other. So think of this as being a molecule cut in half. If the 2 methyl groups are on opposite sides of that, then they are anti to each other. Just hands down, they're anti. If they were rotated so that they were on the same side of the molecule face, then they would be syn. Okay? So also, what you can look at, and I'll put this in red, is that if I draw, oh no, what have I done? If I draw, and I'll do it a fat line, a big fat line through here, do you see how it goes through both carbons? Yeah. So that means that we call that periplanar, because they're in the same plane. Like I draw a line through it and I hit both of them, okay? Now, let's say I draw a different one. So I rotate around carbons 2 and 3 and I get something different now. Whoops. So now I'm looking at something where I've rotated the molecule in a way that it looks like that. Okay, they're basically eclipsing each other. So let's say I have my hydrogen on that one, and a hydrogen on that one, and a hydrogen there, and there, and there. Oops. There we go. So in this case, I draw my line through, and I look. The 2 methyl groups, those 2 CH3s, are on the same side of the molecule, okay? So that means they are syn to each other. I can also take a line and when I draw it down, and you're going to have to kind of imagine a little bit, because really we're looking at it at a slight angle so we can see both of the methyl groups, but I'm hitting both of them, which means this one is also periplanar. So synplanar or synperiplanar. Now let's look at something that would be a little different from that. Oh, what did I just do? Okay. So now let's do one where I have a CH3 there, a CH3 there. Okay. Draw my imaginary little line here in the middle. Now if I'm looking at that one, those two methyl groups are on opposite sides of that line, right? So those are anti to each other. And also, if I drew a line through one or both of them, you'll notice that carbon and hydrogen are the ones that are in line with each other. Or that carbon and hydrogen are in line with each other. They're not in line with themselves, with each other. So because of that, you would call that one clinal. Okay? So as long as you know what the anti and syn mean, and the periplanar and clinal mean, you should be able to look at any of those and tell which ones they are. Okay? Now Bridget says, when you have a three-member ring as an intermediate, why do we see transaddition? Okay. So anytime, let's look at the examples that we saw of something that looked like that. Yeah, Lauren, sometimes by the end of the semester, stuff starts making more sense, so hearing this stuff from the beginning is like, oh, I got that now. You're not the only one that's happened to in life. Okay. So let's say this is some sort of transition state. So, Bridget, let's think of the different transition states we've looked at that look like this. Some of them had mercury with acetates on them, right? Some of them had some sort of halogen that was a halonium ion attached. We even saw one in the formation of an epoxide that looked like that. And when we talked about this, you kind of have to think about what these molecules look like in three-dimensional shape. And that's actually much easier for me to show on this than it is in the classroom. So this is one of the few times where I can show this a little easier. Think about what's on this carbon. I've got some hydrogens, and I'm going to color those green. Right. And then I've got the carbons themselves, right? And I'll just, that acetyl group is quite large because there's a bunch of stuff there, so I'll just make it big. And then the mercury, and mercuries are gigantic, right? Okay? So now I want you to look at that, and let me delete some of this other mess out of the way. Okay. And tell me which looks more likely. That something, some sort of random nucleophile would be able to come through that, or a nucleophile could come up on the bottom where there's this big open space. We talked about this in class, and I showed you guys some examples, but this is what we're looking at. There's like a ton of stuff up here, and there's nothing down here to prevent a nucleophile from coming in and attacking. It's just basic geometry, okay? So if you were to kind of think of this in terms of, where's my cursor? My cursor's like disappeared. If you think of this in terms of like dimensional stuff, right? So if I have a cyclopropane type thing, it kind of looks like that, right? And then if I have this big thing on top, right, that's three-dimensional as well, even if it's one atom, right? Atoms are three-dimensional. So then, I mean, I have a ton of space down here at the bottom, but not a lot at the top. And so it'll attack either at that spot or that spot. But it can't attack from the top because there's a big atom in the way, plus a big-ass charge. I hope that answers your question. Other questions? And Lauren, I'm glad that you understand it now. I have more of a teapot. Keep them coming. Good. I really like it when you guys say, oh, I got it now. Because otherwise, I don't know. I'm like, man, I hope they understand what I just... Because I'll be honest. I draw it, and I'm like, man, I'm doing so good. And then when I look at what... I like kind of sit back and look at what I've drawn, the entire screen looks like this, with like an A and a C and 4 and like alpha. And it's like... That doesn't make a lick of sense when you just look at it. So hopefully when I walk you through it, it makes more sense, but I do what I can. I'm trying. I'm just going to drink some tea. Keto to enol. Okay. I can do that. I'll just keep the screen up. I was really upset when I heard that Microsoft was going to take Paint off of off their computers in like new versions, because I was like, no, I use Microsoft Paint. But apparently it'll still be available as a download, so don't fear, everyone. All right. So Dennis, I'm going to do it this way. Going old school with my structures, just like I'm in general chemistry. All right. Question number 1. This entire unit on chapters 7, 8, and 9, you saw something on there acting as a nucleophile. What was it? You're right, Kenny. There would be like 85 people on Reddit releasing it for free. And it would probably be a better version. All right, hopefully, oh right, the double bond. Thank you, Dennis. Okay, so let's do that thing. The double bond is good at attacking stuff, right? Okay. It just so happens that it's right next to a hydrogen that it can grab. That will take these electrons and put them on the oxygen. And there's another way you can actually show this, where it only involves 2 arrows, but these electrons are going to go and basically form the carbon-oxygen double bond. So if you want to think of it as numbered, you can do it that way. If you, I'll draw that again here in a second. If you do it this way, and like that, that is also appropriate. You're basically just showing the sigma bond forming a lone pair, and then a lone pair forming the double bond. But, there you go. And if you number it 1 and 2 in your notes and stare at that tonight, that'll probably get you where you need to go. Now, similarly, right, we have the opposite way. So at that point, now I have a CH3 at the top, because these are in equilibrium, right? So you can go from one to the other. Dr. Sullivan's messaging me. Hold on. Sorry, I didn't realize the volume was on my phone and that it was right next to the speaker. I apologize if that was a loud noise or something. Okay, so different color. There we go. I'll go back to green. So, okay. Have we seen anything act as a nucleophile? Okay, I turned the volume off and it's still vibrating. That's not helping at all. But it's essentially the opposite of what we just did, right? So hopefully you're looking at that and thinking, yes, I understand this. Now, I think that this one's actually easier to see if you think of the oxygen's electrons grabbing the hydrogen, and then those coming in and those going up on the oxygen. That's a Dr. Mann preference, but both ways are fine. And then Marangeli wanted to know if we can do a reaction adding methylamine or methanamine. Methylamine is like an old school term for it. Methanamine to a carboxylic acid. Well, we wouldn't add that to a carboxylic acid, Marangeli. Are you talking about just doing an acid-base reaction? Because you're looking at a weak base and a weak acid, so that would give you an acid-base reaction. So here I have methanamine and formic acid. Yeah, so that's just an acid-base reaction. Those were the first ones that we did. Like that. Yeah. And I mean, you can think of it, if it was a cyclopentane, then just think of that as an R group. I mean, it could be anything attached to the cyclohexane, or to the carboxylic acid. My husband's an amazing guitarist. I just hear him wailing down there. I'll take another question. I probably look really stupid. You guys can't hear the music, I bet. Make sure nobody's asked any questions in my email. I think I got to everyone's questions that asked something. If I skipped over your if you asked a question and I didn't see it, you know, feel free to ask it again. There's Onyx. I'm covered on the floor with dogs. Reaction with KMNO4. Alright, well there's a bunch of those. Any of them? Well, so a reaction with KMNO4 and H2H2SO4, so you're talking about an oxidation and then a hydration. So KMNO4, let's just come up with some sort of, whoa. That was terrible, let me try that again. Okay. Other than the test in the book? Not really. I mean, if you're doing all the mechanisms that are in the book, you know, if you're doing them for all of the reactions, then, I mean, you've done tons and tons of them, and they're the same thing every time, so you should be fine, right? Like a hydrohalogenation's the same exact mechanism every single time, so you shouldn't really need any others other than that, I would think. Okay. So Marangeli, if I put this in with KMNO4, what is the big question is this in acidic conditions or is it in basic conditions, acidic or alkaline? So you get different answers depending. If you do it with base, you basically add hydroxyl groups to each side. Let's see if I can scroll. You're going to add hydroxyl groups to each side, and they're going to give you syn addition or cis stereochemistry. You could either show them both pointing up or both pointing down. When using KMNO4, do we always get a carboxylic acid? No. Double check your notes from that day because, and double check the ones that basically the stuff, the reviews I have on D2L, because it'll show you that it depends on what's connected and if you're using acid or base. And then with the O3, you don't always get an aldehyde. Sometimes you could get a ketone. It just depends on how many carbons are attached to the alkene. Okay. If I did the same thing under acidic conditions, instead you'd basically be cleaving the bond right there. And cleaving the bond right there, so you'd get a diacid. It's really ugly. Let me see if I can make that a little bit better. There we go. A little better. Okay. And then if we did it with ozonolysis, which is a whole different reaction, you would get the aldehydes. Okay, so that's just identifying and knowing what happens in specific reaction conditions. Okay, so then doing a reaction that has, and I mean this one is straight out of your notes, Jasmine, so this is going to look very familiar. There's not really a way for me to show you a reaction and a mechanism that's different than what you've already seen because they're the same thing each time. So let me just make a cyclopentane there and hope for the best. So nucleophile attacks the electrophile. And so that's going to be, they're attacking the acid, right? And acid is a really good electrophile. I'm going to have to scroll over here, sorry. When you get that, you have a carbocation intermediate, right? So you picked up a proton to put on that spot there, opening it up as a hinge if you were. That follows Markovnikov's rule. And now what I'm looking at is an example where I have a secondary carbocation, but I have a tertiary carbon next to it. So I'd get a 1,2 hydride shift. So I show my hydride moving. You'll notice I'm showing those electrons from that bond moving over. So now I have a carbocation there on the tertiary carbon, and then water will come in and attack. I'm like really running out of room here. Guess I was drawing too big. Okay, now you would have some sort of conjugate base, like so hydrogen sulfate or maybe water will act as your base and deprotonate your chemical there. And then that would give you the alcohol. So let me make that smaller. There we go. So just, here, I'll color code that a little better. Follow this line. That's the way the arrows go. Hopefully that makes sense. And that one, you can pretty easily find that one online too. If you look up hydration using sulfuric, or you can use phosphoric acid. And it's the same if you use phosphoric acid. You're just using phosphoric acid instead of sulfuric acid. So. You are welcome, my dear. Oops. He's getting real weird with the guitar in there. He plays classical guitar where you have like the finger style picking and stuff. And you like beat on the drum or on the guitar as a drum, and it's all kinds of weird. Alright, one more. buddy? You okay? You look like you're going to say something. If Red talks, I'm sorry. He's loud. Smush your face. Smush. Well, Kenny, that's a different reaction. There's like 1,000 different reactions that I haven't covered. If you look on Google, you will find all of them. If you're asking for an unhybridized atom, does that just mean the hydrogens? Hydrogens and halogens. So we're making the assumption that halogens won't hybridize. Sometimes they actually can. You have to experimentally determine that. Terminal oxygens, meaning like carbonyl oxygens, they oftentimes don't hybridize, but I'm giving you guys the go-ahead to make the assumption that everything hybridizes except hydrogens and halogens. All right. Oh, let me tell you guys this. So that I could space things out and make sure that, I basically wanted to make sure, yeah, that it's because Red's gigantic. Hi, buddy. He talks. They're having a good time. Thank you, dear. Tap dancing on aluminum sounds about right. He does know we're talking about him. I don't remember what I was saying. You made me lose my train of thought. Well, Red made me lose my train of thought. What was I talking about? He just does that when he wants attention. Or when he's hungry. Or thirsty, or if he needs to go outside. Oh, right, yes, thank you, Miller. So I made the exam 5 pages, but that's because I wanted to make sure you guys had a bunch of problems so that there aren't as many points per problem. Does that make sense? So the format, wait, no. So the format, in case you would like to know, page 1, that is so tiny. Okay, let me do this thing again. Here we go. So page 1 is material from exam 1. Miller, Marangeli, and Lauren are all like, spacing the test. Page 2. Material from exam 2. Page 3. Are reactions from exams 3 and 4. And there could be acid-base problems on there too. But basically just reactions. And then page 4 are mechanisms. There's 3 of them. And then page 5 should be familiar to you. That is nomenclature. So I was going to make it 4 pages, but then, I mean, then you end up with like problems that are worth 10, 15 points. And so I was hoping if I put more on there, you know, it would be more representative of like the whole class and what you got out of it. So that's it though. I think I'll leave it at that. I have to go cook for my toxicology class tomorrow. I'm cooking for them for their presentations in the afternoon. So I'm going to hop off here, but if you guys have any more questions, you can email me tonight. You know where to find me. Our exam is in the same room that it's normally in. It is from 10:30 until 12:30. In theory, because it's only 5 pages, it should take you about an hour and 15 minutes. So it should not take you all 2 hours, but you get all 2 hours to do it. And then if you're, you know, if you have questions, you can always ask me tonight. Okay? So thank you for the, I'm hoping, productive review session, and I will see you guys tomorrow morning.